For every method we've covered so far and we'll continue to cover, the first thing we do is not really anything for the method, it's something to check to make sure we can do it. So we start off with the check. Check. And the check for this phase line is that the system or the equation is autonomous. Is x prime equal to a function only of x, where by x prime we do mean dx dt. Now, if you have other variables, that's fine. dp dt is equal to a function of p. That's fine. But your slope function only depends upon the dependent, not the independent variable. I'll write that again. That is an autonomous ODE. Okay, so once we've checked that we can do this, we first find all equilibrium points by setting dx dt equal to 0. We essentially find all the roots of our slope function, f of x. Then we create a vertical sign chart. For f of x, labeling stable, unstable, and semi-stable, which is going to be either filled in from the top or filled in from the bottom. You'll see what I mean in a minute. And then C, graph the family of solutions, just to see what this phase line is really representing. Let's do an example. X prime is equal to 2x minus x squared. Okay, so our first step is to set 2x minus x squared equal to 0. And of course, we look to see what we can factor first. X times 2 minus x equals 0. And that gives us two options. X equals 0 and x equals 2. So those are our two equilibrium points. So part B, we create a vertical sign chart. What does that mean? Well, a sign chart is simply when you have a function, you find its roots, 2 and 0. We'll put some open circles for now, and then we'll fill them in as needed. We want to check the sign of this function, f of x, by plugging in some values of x above, in between, and below. Now, a nice trick, an easy way to check the sign on top and bottom is to plug in positive infinity or negative infinity, because you don't have to think too much about what the sign is. If x is positive infinity, we have a plus times a minus infinity, and we get a negative infinity. So at the top, we know it's pointed down. Now in the bottom, x is negative infinity. We have a negative infinity times a positive infinity. And so we have a negative here, right? Plus times a minus. On the bottom, we have a minus times a plus, also going down. And in between, let's pick a number which is easy to plug in between 0 and 2. How about 1? So 1 positive times 2 minus 1 positive. So now we've played the sign chart and we use the information to fill in the dots. We know that 2 is stable because it is absorbing, or the solutions are converging towards it from both sides. Whereas 0, x equals 0, is unstable because the arrows are pointing away from it, or the solutions are diverging from it. So that's the sign chart. Let's wrap it up. By graphing the family of solutions. Now, what does this mean? Well, instead of drawing a slope field, which is a lot of work to do by hand, we are going to instead follow the arrows towards these equilibrium points, or away, depending on what they are. So I'm going to take this phase line and extend the equilibrium points outward, and then take some possible solutions that are converging towards it. There's one, there's another, converges towards it, and it will converge a little bit more gently than what I did here. Be careful. Converge asymptotically. Converge asymptotically like that. Now below, we have an let's skip the middle part first. On the very bottom, it's pretty simple. You're diverging asymptotically. And in the middle, you're diverging asymptotically and then converging asymptotically. This is where we get that S-shaped curve to it. And then we can fill in a few more of it. Diverge or converge similarly. Now, one thing to point out is I'm being very careful to keep the same slopes across. Even though I don't know what the value of those slopes are, I have an up arrow. What does that tell me? How do I know? Is it a 2? Is it a 3? What do I know? I don't. I do know it starts at 0, it's positive, and then it's 0 again. Oh, so the slope starts out 0, is positive, and then is 0 again. So it must increase and then decrease. That's where I get that S shape from. And it's going to increase and then decrease. That S shape will be the same. I mean, not quite the same in my drawing, but it's very close. Where I have copies of that S shape again and again and again and again. And that's because of the autonomous nature of the differential equation. That slope should not change with time. Okay, so that's how we draw and use phase lines. Now, going through part B is usually enough to create them. Part C, though, really goes home and shows that you know what it means. Shows that you understand how the solutions behave around this shorthand notation. And that's really important about this course, is that we will often develop these very simplistic shorthand notations. But if you don't understand what they mean, then the shorthand is useless. So make sure you know the shorthand for a phase line, part A and B, and then part C, what that shorthand means, and being able to write or draw out the solutions from your phase line.